All right, so here's the problem. Let's say we have some uranium-235 in some ore, and the uranium-235, of course, turns into lead-206. That's a very special isotope of lead. You don't find that type of lead around the world, except for the lead that comes from uranium-235. So what we're going to do is we're going to assume that in the ore, all the lead-207 came from the uranium-235. Now, uranium-235 has a half-life of 704 million years. All right, so here's our problem. So when you dig up this ore, 65% of the ore is in the form of lead-207. All right, so how much time has, what's the age of the ore, right? So the age of the ore is what T is. And so T, of course, is, and we had this from chapter 13, it's the half-life times the fraction, the natural log of the amount of uranium that still remains divided by the amount of uranium that you started with. The N is the amount of the radioactive substance. And this is the amount that you started with, divided by negative, this is just the logarithm of 2, so we're just going to round it to 0.693. That works just fine. All right, so we have a little bit of work to do. If 65% of the ore is remaining, if 65% of the ore, when you dig this up, is lead-206, then that means the remaining amount, N here, you have to have 100%, because it all came from the uranium-235. So the amount of uranium-235 N here is going to be 100% minus 65%, or 35%. Right? So doesn't that make sense? So N in our case, here, let me write this out here. So N, why isn't it writing? Oh, I'm in the, okay. So N, sorry. Oh man, it always does that. All right. So let's try this again. So N is equal to, so it's, it's 100%. I'll just do it for completeness. 100% minus the 65%. All right, 65%. All right, so that gives us that's of course 35%. All right, so that's what N is. N is 35%. And what it really is it's 35% of the original amount. So 35% of the original amount. So that's really 0.35 N sub 0. That's what N is equal to. All right. So that's ultimately what you need. All right. So and you get that from the fact that 65% of it has become the lead-207, which means, of course, 35% of it is still uranium, the radioactive uranium-235. All right, so here we go. So we can put in 0.35, right? So 0.35 times N sub 0 divided by N sub 0, right? You don't really need to know what the N sub 0 is. I mean, you could figure that out, but it doesn't really matter. All right, so we're going to do this. So it's really just the natural log of 0.35 divided by negative 0.693. Here, let me rewrite it so it looks a little bit better. All right, so it's going to be the half-life, which is 704 million years. So it's times 10 to the 6th years times the fraction, the natural log of 0.35. Right, 0.35, and of course we got that from the fact that 65% of the ore is now lead-207, right? And then you divide by negative times 0.693. All All right, so here we go. Let me get my calculator so we can do this together. All right, let's see. So I'm going to move that over a little bit so you guys can see this. All right, so this is the calculation. All right, so now this calculator is a little bit weird in the way that you have to do this. All right, so anyhow, it's 0.35. All right, I guess I should step back. All right, so if you go 100 minus 65%, right? So that's how we get the 35%. So 35%, of course, in numerical form, as a regular number, of course, is 0.35, right? So 0.35. I take the natural log of that, right? So that's this number right here. So that's the natural log of it divided by. So you do for this calculator you do 0.693, and you hit the negative, otherwise it doesn't do the right thing. Anyhow, you multiply that, all right, and so you get this number, and we're going to multiply that times 704 million years, all right? So times 704, and million, of course, is times 10 to the 6th. All right, so there we go. All right, let me move this over just a little bit so you give us room. I'm going to write the answer right here. So there it is. All right, so here's the decimal. We'll go two places past the decimal. All right, so on Blackboard, it would say rounded to 2 places past the decimal. So here's the decimal right here. So 1, 2, 3, 1, 2, 3. And then there's another 3, right? So now we're up to 1.07, right? Because it's 6. Okay, so it's going to be. So the answer here is 1.07. So 1.07, right? Because it's 6 billion is times 10 to the 9th. Right, and that's so, and of course that's in years. Remember, but in Blackboard you just write the number. All right, so that's what you do is 1.07. If it said rounded to 2 places past the decimal, and then you have to use this E9. All right, because that of course is what this number is. All right, so that's the way you enter that into Blackboard. Right, so let's see, 1, 2, 3, 1, 2, 3. 1, 2, 3, so that's times 10 to the 9th. All right, so there's a good example for us. All right, let's here. Hold on. Oops, didn't mean to do that. All right, let's do a different problem, although very similar. So potassium-40 is a radioactive isotope. It turns into argon-40. Argon is an inert gas. The half-life of potassium-40 is 1.3 billion years. All right, so there's the half-life. Let's draw that. All right. Suppose you dig up some ore and you find that 37% of that ore is argon-40. All right, so the zero didn't come out very well. But if 37% is argon-40, and all of the argon-40 came from the original potassium-40, so here, we can do this little game again. So remember, we're trying to figure out what N is, right? The amount of potassium-40 that remains, right? So that's going to equal, of course, that's going to be 100, because there was 100% of the potassium-40 minus what is now turned into argon-40 minus 37%, right? So we'll leave these as percents right now. All right, so of course that would be 63%. All right, 63% is still in the form of potassium-40. All right, and so now we can do our formula. So this is T is equal to the half-life, which is 1.3 billion years. I'll just do E to the 9th years. And and then of course it's the natural log of, remember it's n, here I didn't write that, but it's here, I'll do it over here. It's the natural log of n over n sub 0, right? Where n is the amount remaining and n sub 0 is the amount that you started with. All right, so it's remember this 63%. This is 63% of n sub 0. So see that the n sub 0's cancel. So it's 63%. So point 63 n sub 0 divided by n sub 0, right? And the n sub 0's cancel, and so you're just taking the natural log of 0.63 and you divide by negative 0.693, right? Remember, we always divide by that same number. All right, so let's do this. I'll get my calculator here. Oops, scoot it over a little bit. All right, so there's my 63%, sorry. So it's going to be 0.63, all right, the natural log of that, and then divide it by 0.693. Now, so most of your calculators, you have to hit the negative first, but anyhow, this one is kind of weird. You got to hit it afterwards. So So I'm dividing the natural log of 0.63 by negative 0.693, and so that's going to give me what this fraction is. So equals, and so then we multiply that times 1.3 billion years. 1.3 and billion, of course, is here. So exponent to the 9th. All right. So we'll figure out how many it is. All right. So it is. So if we, you can see not even since it's only 37% of argon 40, not even one half-life has gone by. All right. So let's just observe that, right? So it's going to be something less than 1.3 billion years. All right, so and indeed it is, right? So I move the decimals right here, and so I go 1, 2, 3, 1, 2, 3. So that's millions. So this is this would be 860. Let's go 2 places past the decimal. So this is how you'd write this in Blackboard. So it'd be 8.67, right? If I went 2 places past the decimal, times 10 to the 8th. All right, does everybody see that? So 1, 2, 3, 1, 2, 3, and then 1, 2. All right, so that this number, the time that has gone by, it'd be 8.67. So 8.67 times 10 to the 8th years, which of course, remember, times 10. The billion is times 10 to the 9th years. This is substantially less than that. Well, maybe not substantially less, but it's certainly less than a billion years, right? This is 866 million years roughly, or 867 million years. So there's 2 good examples using percentages. All right, so I just wanted you to be able to see that, and have a good example like that. Two good examples like that.